So welcome, this is third section in this four-part section on oscillations, waves, sound and interference of mechanical waves. So we're on sound. And if I look here, let's look at our big ideas. Let me find my pen. So our big ideas, periodic sound waves have different speeds in different media. So the media for sound, we might think of sound as being in air, and that's true. But we're also talking about sound going through solids, goes through metal, goes through fluids, goes through different densities, different types of media. And it turns out, and you can kind of get it, if I set up a sequence of people in a line, and rather than, supposing they're all facing the same way, and I have each person put their arms on the shoulders of the person in front, and I say, hold your arms really rigid, and I go to the back and I push the back person, very quickly the person at the front is going to feel that energy. But if I say, let your arms relax, just make sure that you kind of like you squish and then you push back. But you end up with your arms stretched, but you squish and then you push back. That's the thing. You squish and then push back. And I push the person at the back. You see how the energy will take a lot longer to get to the front person, because each person took time to squish and then push back. So the physicality of the medium will have an effect on the velocity of the energy going through, which is the velocity of the sound waves. So it's not surprising when we think about it conceptually that different mediums have different speeds of sound in them. We can see that a plot of particle displacement versus position along a wave is 90 degrees out of phase with a plot of the medium density versus position along the waves. I'll show you that in a minute. We can define a relationship between the wave's pressure, amplitude, and the medium's density and the wave's velocity and amplitude. I'll talk about that in a minute. Periodic sound wave intensity can be measured in watts per square meter and decibels. That's really important. I need some way of measuring the intensity of sound waves at a given position. And then if a source detector distance changes while a sound, let's say a simple sound like a one note, is being emitted, a listener would hear a different note. And we've seen that with cars. When a car's coming towards us, the engine sounds high-pitched. When it's going away from us, the engine sounds low-pitched. You noticed that? So that's called a Doppler effect. And that's a very far-reaching phenomenon that we apply to light, and is used in astronomy, and is used as bedrock evidence for the fact that the galaxies are all moving away from us, or most of them anyway. Andromeda's coming towards us, but yes.
What did you call that effect again?
Doppler, D-O-P-P-L-E-R. 1P or 2P, I can't remember. Oh, 2 P's, I guess, yeah. And then if a source travels faster than the speed of sound in a given medium, then we get a shock wave. And that's Mach numbers. So you can see, this is important. For me, that's important. That's important. That's important. These two, they're like not so important to me, apart from conceptually, I'd say. But they're there. So let's begin. So first of all, we kind of know, because we did it with the string, that the velocity of energy along a string is not a sound wave, we're talking about a transverse wave here, is the tension versus the mass per unit length. We know that. And if I generalize, the tension is an elastic type property, and the mass per unit length is an inertial type property. Remember, Galileo said basically mass is inertia. Yeah. And it makes sense, because if I have more inertia, I have more sluggishness, so the velocity should be lower, and if I have more elasticity, then my velocity should be higher. And the square root, as I said, I don't know about. I can't perceive that as being obvious, but it's there. If I find the sound equivalent for this, then I do have an equivalent relationship. And what it is that the better way of describing the elastic property of a solid or a medium is its bulk modulus. And the inertial property of a medium would be its density. Mass per unit volume. Newton per meter, per square meter for the bulk modulus. Okay, so bulk modulus, remember that from Physics 1? You had the thing with the, you had the cube of the stuff. We started off and what we spent most of our time talking about was a piece of wire and stretching it. And whose modulus was that? Was that the Bonaquisti modulus? I don't think so. It was Young's modulus, yeah, so that was Young's modulus. And then we had the, how well can I push over a textbook? And what was that kind of modulus was that? It's like a shear modulus. Yeah, shear. Wind shear is when winds go sideways kind of thing. This is a shear modulus. And then we had this thing with a cube where we put it inside a container and we increased the pressure. And of course the volume got less. It reacted. Stress over strain, remember that bit? And we got the bulk modulus. So we're talking about this guy, the bulk modulus. And each material has a different figure of merit. It's a figure of merit. It's a bulk modulus. It's a figure of merit. So we can look it up in the engineer's handbook and we can look at the material and we can look at its density, and from that we can predict the velocity of sound inside the material. And all right, so we know even for gases, as we change the density, we'll get different speeds. At the extreme, a good trick is always to say, what happens at the extremes? Well, I'm not sure I want to go to the extreme on that. Anyway, so it is affected, and density is affected by temperature, and so we can talk about the velocity-temperature relationship for gases. We use this quite often. What we have is we have a standard number which is 331, and it's modified by the temperature effect. So it's square root of 1 plus Tc over 273. When I was a student, my book just said T over 273. And I'd get into exams and I'd go, well, is that centigrade, or is it Fahrenheit, or is it Kelvin? Pretty sure it's not Fahrenheit, but could be Kelvin, could be centigrade. And so I kind of later on, much later on as it turned out, I realized I own this equation. I can't put down Z because I just want to be that way. Nobody will understand what I'm talking about. But I can call it T little c to remind me that it's in degrees Celsius. So take ownership of your equations, you know? You can't change the letters so much that nobody understands what you're talking about. Well, that I don't understand what you're talking about. But you can put subscripts, you can put these things so that you don't get things confused and you actually get a bit more information. So just practice writing this down as TC. That's why I put it in the notes this way. Cool. So, I'll do the first, and then you guys, we'll see about the second. So sound propagates through air that has a bulk modulus. So my bulk modulus is equal to 1.2 times 10 to the 5 Pascal. Remember, newtons per square meter is a Pascal. And it has a density. Density is equal to 1.2 times 10 to the, well, it's just 1.2 kilograms per meter cubed. So what is my velocity going to be? My velocity is my elastic property over my inertial property square rooted. So that's square root of b over that, which equals the square root of 1.2 times 10 to the 5 over 1.2. I can do that because I'm in SI units. I mean, I do check on that. If I'd given you it as kilopascal, then you'd have to convert it because it's 1,000 times bigger than the number says. And if I gave you it in grams per cubic meter, you'd have to do a conversion, you know? So this is going to be V is equal to the square root of, well, 1.2 divided by 1.2 is 1 times 10 to the 5. And I can even do that. Oh, got to do the square root of it. So V, I can't do that in my head. So that goes second square root 1, 0, 0, 0, 0, 0, enter. And I'm getting 316.22. And even though I quoted my numbers with 2 significant digits, I'm letting it run because I want to be able to see that you got the right answer. I don't want to have to give you difficult numbers to get a highly resolved answer. So just give me, bend the rules and give me an answer that's a couple of decimal places is what I ask. Okay. Okay? Can you do the second one for me, please? Yeah, let's have a look. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I've got 18 people. I know that some people don't like to do it, and if you don't like to do it, then put down E, But I do advise you to do it. So I'm sorry I forgot to turn the video back on, but here's the second version that we did in front of the class. And what I was saying was that these are realistic numbers. So the speed of sound through granite is over 10 times faster than the speed of sound through air, all other things being equal. So, on this next one, let's do this next one. What is the speed of sound through air at 0 degrees C? So I'm going to say the temperature of interest is equal to 0 degrees C. And I know that V is equal to the magic number is 331. And it's modified, so we have square root plus. As the temperature goes higher, the speed gets higher. Okay, so I have 1 plus Tc over 273. So V is equal to 331 square root of 1 plus 0 degrees C, 0 over 273. So this equals, well, that's going to be the square root of 1. 331 times the square root of 1, which equals 331 meters per second. And the next one, what with a different speed? Tc is equal to 38 degrees C. V is equal to 331 square root of 1 plus Tc over 273. B is equal to 331 square root of 1 plus Tc. Well, that's 38 over 273. So that's going to be, and I just work out my answer. 353, so thank you, 353 degrees, meters per second. Cool. So we're in business. Yeah. Cool. This next bit, as I say, I want you to focus more on the conceptual bit than on the realistic bit, than on the mathematical bit. For instance, in my wife's department, where they talk about speech, sound, they do audiology and they do speech therapy. My wife's a scientist. My wife's kind of like she basically did English, French major. She then did a PhD in linguistics, but it was really one of these interdisciplinary PhDs where it was cognitive sciences. Half her research group were computer people. And then she did a postdoc in communication sciences and disorders. Her PhD was on the intelligibility, well, her PhD was really on predicting the difficulty of one native speaker learning another language. If I learn French, can you predict what sounds I will have difficulty producing? What sounds I'll have difficulty hearing? Turns out, unless you're exposed to certain sounds when you're an infant, you don't hear them. Your brain doesn't recognize them, so you don't hear them. So it's an amazing system. And so she's faced with actually teaching a whole bunch of people who want to be healers and help people hard science. And so she has to find some interesting issues. Graphs are very important. And one of the issues is you can plot sound in a whole bunch of ways. It's very abstract if you think. We don't draw these diagrams. This is the visual. And nobody draws that because it's a real pain. Doing all those dots take hours, So we have what are condensations. I don't really like that term because that implies droplets of liquid to me. They don't mean that. So I prefer to use the term compressions. And they have rarefractions, like a rarefied atmosphere is thin. A rarefraction is where the air's become thin because the particles have moved away. And clearly you have high pressure at a compression region, and you have a low pressure at a rarefraction, and there's the average pressure before you begin. So as you hum down a tube, or in this case I'm moving this piston backwards and forwards at a regular frequency, I will get these patterns. The wave, I get these patterns, let's say, and I can plot a graph of pressure versus position, and I get something that looks like that. It looks like a sine curve. It looks like a transverse wave, but that's because it's a graph. It's a abstraction of the data. The actual physical system is there, but we plot a graph of it. There's other times when we're interested in actually looking at what happens with the actual individual particles or the families of particles. And so you can cheat a little bit. All particles are moving all the time, but we can say, let's say the particles are just hanging around in space beforehand. And then we do this thing to them. What would happen? Well, if you think about it, the particles in the very middle of the compression don't need to go anywhere. Other particles are going to come to them. And the particles in the very middle of the compression don't need to go anywhere because particles are going to leave them. So those two particles have zero displacement. Those two families of particles have zero displacement. I'm sorry, I did the compression and compression. In the middle of the rarefraction, those guys get left, and these guys get approached, and these guys get left. No displacement for those particles. What happens in between is these particles, well, they became rarefractions because the particles moved. And what happens is that if we take the middle of that bit, the particles moved in a negative direction. And if we look here, these particles moved towards the compression on that side. So if you look at the middle of that bit, those guys moved in a positive direction. And you can even say, if you're kind of close to the compression, you don't move much, but you move a little bit. And if you're kind of close to the middle of the rarefraction, you don't move much, but you move a little bit. But if you're in the middle point of this in-between, you move a lot. Isn't that kind of like fascinating, the detail they can get out of it? And so they can say, well, the expression for the displacement, I'm sorry I'm showing these things, for that guy is a cosine function. Look at your graph. And the expression for the pressure is a sine function. Let's look at that graph, yeah? And fine, okay. I'd like you to know that they are out of phase. I'd like you to know this bit. For here, we can go and say, well, we can define a thing called a pressure amplitude, and the pressure amplitude is equal to something which depends upon the density, depends upon the speed, depends upon the frequency, and depends upon the maximum amplitude. And frankly, you don't need to remember that equation. I might give you it and say, hey, how does the pressure max go with the frequency? But, just be able to recognize the symbols and use your math skills. And I'm not even going to do this because I would not ask you a numerical question on this bit anymore. When it was on the equation sheet, it was fair game, but not anymore. So know that diagram, be comfortable with it, and yeah, if I throw the equation at you, I will call it a pressure amplitude. I'm not just going to put symbols up there and say, what does this mean? I'll say the pressure amplitude is given by delta P max is equal to, Okay. Relate these things. And they're your math skills. They're like, but you don't have to commit that one to memory. Because I don't. I kind of use the principle, if I don't know it, I don't think you need to know it. And if I know it, I think you should know it, Because you're going to be an engineer. And you're going to be my equal very quickly, So in knowledge, you're already my equal in so many other ways. But This next bit is really important, and it's about the intensity of sound waves. And it's really important because it keeps coming back. It's like the intensity of light, the intensity of radiation, the intensity of sound, the intensity of a whole bunch of stuff. The trick is that the energy is created in a given time, energy per second. So this source of energy here is creating an amount of energy in a given time. How much energy per second? Joules per second. And that is power, not pressure. Notice we just changed our symbol. Well, no. We kept our symbol from one page to the next. We've completely changed our meaning for the same symbol. And that's just like, hey, that's the way it goes. We ran out of letters a long time ago. So P stands for power, P stands for pressure. Go figure. Just look at the context. You don't get, if I say my dog, I can't think of a good expression, dogs bark, you don't think that they create kind of like wood chips. You go, no, dog barks, it makes a sound, tree has bark. It's a wood chip. You don't get them confused. It's context. So same goes for this. So that energy per second is spreading out. Imagine dropping a pebble into a pond and you see a ripple. And then as the ripple spreads out, it goes over a bigger and bigger circle. Same energy in the ripple is spreading out over a bigger and bigger circumference. Well, in 3 dimensions, the sound is doing the same thing, spreading out in all directions. So that energy has to spread out over the surface of a sphere. And so the take-home is that the intensity is the power of the source divided by the area that power is spread out over, that energy is spread out over. So I say the intensity is power per area, and for a spherically symmetrical system, it's going to be the area of a sphere, which is 4 pi r squared. That's one of our equations today, isn't it? So this is why we're learning them. So you don't have to, what is that? You just know it's 4 pi r squared. This is really, 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 really important. And I can mess with you. The intensity is about the power of the source and the sphere that the listener or the microphone sits on. Now, maybe my microphone or my ear has a certain area. And I can ask you, oh, how much energy per second goes through that area? So I'm mixing things up. I've got one area which is the area of the sphere, and I have another area which was the area of the detector. And so it's easy for people to get confused. The intensity on this sphere is the power of the source divided by the area of the sphere. Now, if I know the intensity at that point, I can say, oh, the power going through my detector in joules per second will equal the power, the intensity, which is in watts per square meter, multiplied by the area of my ear, if you like. So here I have my intensity is equal to the power of the source divided by the area of the sphere. And having found that, I can say, well, the power going into my ear is the intensity at my ear multiplied by the area of my ear. So I can, it's visualizable It's just I'm throwing a second area in just to see, can you distinguish between these things. Can you see that pattern though? The power of the source creates an intensity at my ear. Depends upon the area of that sphere. And having got the intensity at my ear, the power going into my ear depends upon that intensity multiplied by the area of my ear opening. Okay, so watch out for that. I find that, and another thing that's just on me is, I can ask you for the power going into here. Let's say instead of asking you for the power going into there, I ask you for the energy that goes in your ear in 5 minutes. The amount of energy is equal to the power multiplied by the time that the power is applied for. So, and I see this often. If I ask people to work out the power, often people, maybe 7 out of 10 people will get it. Maybe 8, maybe 9, depends on the semester. If I ask them, well, how much energy goes through in 5 minutes? The success rate falls off. And it's always stunned me why, because it's a simple relationship. And what I think happens is we do power at the very end of this bit in Physics 1, and then we keep touching on it from then on, but we never really live with it for any length of time. So watch out for that. It's like, you know, when there's a time when you calculate power, I can very easily, rather than saying calculate the power, I can say how much energy is this in 5 minutes, 5 seconds, 15 seconds, 5 days. And it's just that simple conversion. And then the other thing I see, which is I find really frustrating, is that if I did that and said 5 minutes, sometimes people will put 5 in for that. They're no longer in SI units. It's like, oh man, never, unless you have a really good reason, always be in SI units. You know, the exception should be not the rule. So a source of sound originates energy in all directions. The source radiates, so is my visualization. Source radiates. It goes, the delta E is equal to 10 joules. And each second, so my delta T equals 1 second. That's what that says. The source radiates 10 joules of energy each second. That's what that's about. And then it says, what is the intensity of sound at any point that is 2 meters away? So let's just make a point of interest. I don't want to call that P. That's a bad choice. I'm going to just leave it as a dot, and that's 2 meters. So we say, well, I want intensity. Let's put intensity equals question mark. So my intensity is equal to my power over my area. If you like, area sphere, so that I'm really not going to mess it up. So power equals, so power over 4 pi r squared. So my intensity is equal to, and my power equals delta E over delta T. Joules per second is a watt over 4 pi r squared, which equals 10 over 1 divided by 4 pi times 2 squared. So my intensity is equal to 10 over 2 2s are 4, 4 4s are 16, 16 pi, which equals, I'm going to get my calculator, and I go 10 divided by 16 equals, divided by pi equals, I'm getting 0.199 watts per square meter. Now, just a little by the by. Not a fair number of people, but a few people on this question would give me 10 divided by, would give me 1.96 watts per meter squared. Can you guess what they did to get the wrong answer?
They didn't keep the pi with the 16.
Yeah, they didn't use parentheses.
Pi 10 over 16 divided by pi.
They said 10 divided by 16 pi, literally with their keys. And the calculator assumes that that is 10 divided by 16 multiplied by pi. So it goes 1.6 times 3.142. So you've got to do 10 divided by parentheses 16 times, or 16 pi. You can get away with that. or 10 divided by 16 times pi. You can do that. Or what I tend to prefer is 10 divided by 16 enter. And then divided by pi enter. So it's worthwhile. It's not just this calculator. It's like TI-83s. They all do it. So you've got to watch out. It don't catch you very often, but it catches the people it gets all the time. So they're consistently losing points over it. So watch out for that. Okay. And along came Alexandra Graham Bell, inventor of the telephone. Actually was interested in helping people who could not hear very well. And he invented a scale. He invented a scale for intensity. Why on earth would he do that? So this is if you take a intensity meter out into the field, and it's intensity, so it's in watts per square meter. How much power goes through a window, that's what it's measuring, watts per square meter. And you do different things. You find that your ears are amazing. The smallest sound that somebody can hear is about 10 to the minus 12 watts per square meter. A watt is a joule a second. A joule is a Newton meter. Lift an apple onto a table. That's a joule. Do that every second. That's a watt. Don't know where I'm going with that. Hold on. No, I don't know where I'm going with that. Sorry. But it's not much. And at the other extreme, we can actually withstand, you might not like it, but we can withstand 10,000 watts per square meter. Imagine that's like having 100 watt light bulbs. And not just feeling the light, but feeling the heat that comes off them, because the light bulb is only 3% efficient in light. It's 97% efficient in heat. So tremendous power going in your ear, and it still works. You can't make a machine as good as that for the scale of its reaction. If you make a microphone, there's a whole subculture. I mean, musicians, I think, know this. Some microphones are pleasing, and other microphones are not pleasing. You wouldn't dream of using the same microphone you use for, you know, recording messages on your iPhone, for micing up a concert. And somebody playing with a classical piano might prefer a different microphone to somebody who's singing jazz, because it's different. Your ears can handle all that, you know. It's kind of, you can still hear jazz, you can still hear, you know. So amazing biological system, amazing system, and amazing dynamic range. This is basically 10 to the 16 dynamic range. Imagine getting a skyscraper and dividing it up so that if this is 1 unit, you have 10 to the minus 16 of that unit. I mean, it would be the atomic level, you know. It's like phenomenal. Massive dynamic range. A rustling of leaves, well, the smallest sound we can hear is about 10 to the minus 12 watts per square meter. Rustling of leaves is a factor of 10 more intense. Whispering is a factor of 1,000 more intense. A vacuum cleaner would be 10, 20, 10, 100, 1,000, 10,000, 100,000, a million, 10 million times more power per square meter. Power mower, and so on. 1 billion times. It just goes on and on and on. Tremendous dynamic ranges. Jackhammer, etc. We tend to have hearing damage round about there for extended periods of time. OSHA has standards for this. If you are exposed to that for hours, you know, on a regular basis, you will have hearing damage. How many of you were told by your parents to go out and mow the lawn? How many of you had parents who gave you ear protections?
Headphones.
You can sue them. Okay. You can get even for that. Dads? So it's an issue. If you get into a very loud sound, you can actually have immediate hearing loss. So there was a classic story in Britain about, there was this group that were always incredibly loud. They were one of like the very early, really, really, really loud groups. They played 3 chords over and over, and the tunes were like 20 hits, and they were like the same 3 chords, but it was like just different orders, but it was like really catchy, but it was really loud. And at the my generation was the generation which rushed the stage, and so they'd have police on the stage to keep you off, even if you weren't going to rush, to have police there because it was like a status symbol. And they employed these fire guys to kind of like, hey, stand on the stage. And they put them in front of the speakers, and they said, here's some earbuds. And the guys thought they were joking, so he just didn't put them in. And he said he was listening to it. It was incredibly loud. And then all of a sudden, it seemed like they just unplugged the amplifiers. And he thought, well, that's a relief. And then he looked, and the crowd was still screaming, and he couldn't hear a thing. And he damaged his hearing. It came back, but it damaged his hearing. And there was a student in my class was in the military, and they were doing sort of artillery fire. And there was something like he was distracted, and he didn't see that the gun, not his gun, but the gun next to them was going to fire, and he didn't have his hearing protection on, and it damaged his hearing. That one thing just damaged his hearing. I have a hearing loss, and my hearing loss was caused by me listening to loud music on headphones while I was in college. I was a good neighbor, didn't have my stereo up full, had my headphones with my stereo on full. And about 5 years ago, I started realizing there's a unusual hearing loss. It always gets worse as you get older, but unusual hearing loss. It's called a 5,000 hertz notch. I damaged the little hairs in my ears that respond to 5,000 hertz noise, and what happens is it should like fall off with age, and what happens in my case is it's kind of like gone like that. And unfortunately, in that 5,000 hertz notch, it's where there is consonants. So B and P and etc. V, I have a tough time with. And when you say to me, look at that ball, I don't think you said, oh, look at that fall, or look at that vol. So I get it from context. But my daughter, we were watching Dora the Explorer, and they have Spanish words, and they were talking about the cow vaca. I'm encouraging my daughter to say vaca. Oh, she's learning Spanish kind of thing. And I'm going, vaca. And she goes, no, Dad, vaca. And I'm going, yeah, vaca. And she goes, go and see the doctor. And my wife had told me that I had a hearing loss, and I told her she was mumbling and never do that again. And I went for the hearing check, and that's exactly what I had a hearing loss. And I said, oh, no, I worked in industry. I was around whining turbomolecular pumps. It must have been caused by that. And the audiologist said, absolutely not. He goes, OSHA is all over that. They regulate how loud that whining can be. No one regulates how much you turned up your stereo. And he said, you listened to loud music on headphones. And I said, well, yeah. And he goes, yeah, there it is. And that's what it's caused by. And I said, but everybody listens to loud music on headphones. And he says, well, they do now because we have those earbuds. He said, I'll never be out of work. I just got to wait for people to get old, And it happens really quite quickly. So please do not turn the volume up full and listen to your music. Certainly on headphones. Please don't do that. Because the pressure is confined inside your ear canal, and you're just weakening those little hairs in your ear, and when you get older, they're just going to die. So, okay. So So much for the sermon. Now, the problem with this is we're never very good at powers of 10. We don't realize the significance. And so Alexander Graham Bell said, let's get a system whereby we can represent this as a log scale, basically. And so he developed this, which is we take the intensity in watts per meter and we divide it by 1 times 10 to the minus 12, and we multiply it by, we take the log of it and multiply it by 10. So here's the example. So at a point of interest, the sound from a vacuum cleaner has an intensity of 1 times 10 to the minus 5 watts per square meter. So this was before I used to get you to learn that it is 1 times 10 to the minus 12. In the book it was as I naught. But you might as well just learn it's 1 times 10 to the minus 12. What is the sound intensity? So it's 10 times the log of the intensity over 1 times 10 to the minus 12, which is 10 to the minus 5 over 10 to the minus 12, which is the log of 10 million, which is 7, which is 70 decibels. And here's the example of it. At the point of interest, the sound of whispering is, so we say our decibels is equal to 10 log I over 1 times 10 to the minus 12. So B is equal to 10 log I, in this case, is 3 times 10 to the minus 9 over 1 times 10 to the minus 12. So B is equal to 10 log 3 times 10 to the 3. And I don't know that. If it was 1 times 10 to the 3, I'd know it's 3. But I don't know that. So I'm going to go and turn around and say log 3 second EE to the 3, close my bracket, and then I'm going to multiply that by 10, so I get 34.77 decibel. Cool. How many people go to the movie house and find the sound too loud during a movie? Yeah. I had a student at USF who had a decibel meter and would go around and check. And he'd go, I want to see the manager. So he said these high schools, at night it's like there's like a high school student was in charge of the movie. You know, it wasn't this old guy. It was like, you know, the old guy wants to go home. So basically I have a relatively young guy. And he said often it was younger than me. And he said, do you know that you're showing, this show is, the decibel in that place is this level? And I go, no. And he says, you got to turn that down. And he goes, they'd go to this projector who was like even younger, and the projector would turn it down. And there's no, I was looking and there's no ordinance that I can find for how loud a movie cinema should be. If you go to Ybor City, there's an ordinance that says how loud it is on the pavement compared with inside the club. So they can have all the doors closed and have it really loud inside, but they can't have all the doors open and have it really loud because that affects public space. But inside a movie house, they can make it as loud as they like. But, you know, it's not good. And some people are more sensitive than others. I think I'm quite sensitive to it because I just cannot stand it sometimes. But I'm too shy to go and complain to this high school guy about how loud it is. Man, I got to work on that. I'm running out of time a little bit, so what I'm going to do is, I've still got time. It's all right. I'm going to do this. 16 minutes, yeah, go on. So if I have a source of sound, yep, and you hear the note, don't you? Didn't mean to do that. You hear the note. You hear the same note that I hear because we're in the same room. But if I move this source of sound towards you and away from you, you will hear one note as it approaches and another note when it leaves. Can you hear that? And to some extent, if I go faster or slower, can you hear a difference in the pitch there between those? So that is the so-called Doppler effect. And what we're doing is we're scrunching the compression waves up, if you like. We're changing the wavelength of the energy. So here I have a source of sound which is stationary and a listener who is stationary, and I'm sending out, if you like, one compression. There's a delay, but the compression arrives, and then a little bit later I send out a second compression, and I send out a third compression, and I send out a fourth compression. And if you like, that distance there is the wavelength of the sound. There's a delay, so I hear, if I imagine going click, 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 I send out click, 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 and I hear click, click, click. There's a delay, but I hear the same thing. If I actually move the source towards the listener, then there's no difference for the first wave. It takes a while to get there, but it gets there. But the second wave has less distance to travel because I moved towards. And the third wave has less distance to travel because I moved even further towards. And the fourth wave has less distance to travel because I moved towards. And can you see how I've compressed the wavelength there? I made them closer together. Well, V equals F lambda. Constant velocity, because that depends upon the medium. If I make the wavelength smaller, I make the frequency higher. So if a source of sound is approaching, the frequency that you hear will go up. If I move this source of sound away, then the first wave is not affected, but now the second wave has a further distance to travel, so it's more delayed, and the fourth wave has a more delayed, and the fifth wave has more delayed, and the wavelength is longer. If you make the wavelength longer, then the frequency is decreased. So low frequency when it goes away. And you can hear that with a car. When it comes towards you, it's high pitch, and then when it goes away from you, it's low pitch. 4 possibilities. Approaching source, stationary observer. Receding source, stationary observer. Stationary source, approaching observer. Stationary source, receding observer. 4 equations. Oh man, what a pain. 1 equation. The frequency observed is equal to the frequency of the source multiplied, modified by the speed of sound in air plus the velocity of the observer divided by the speed of sound in air minus the velocity of the source. So the first thing I've got to do is remember that V is the speed of sound. Vs is the source speed. So I've got to know what my symbols stand for. And it kind of, what I do is I picture somebody screaming on the top of a pickup truck. So the observer is on top of the source. I don't know. Somehow I try and remember the observer is on top. I could do, it goes alphabetically and O becomes before S. Just figure some way of remembering. And then positive on top, negative on the bottom. The other way is you say, do I expect the frequency to be higher or lower? And do what you need to do to get it higher or lower. That's another way. The way that I distinguish the sign of these guys is if the observer is approaching, it's a positive V0. If the observer is receding, it's a negative V0. If the source is approaching, it's a positive Vs. If the source is receding, it's a negative Vs. And let these operators in front take care of the math. So approaching something, it's a positive sign. There might be a positive sign in front of it. There might be a negative sign in front of it, but just recognize that. And just play with it. Make sure you understand where these 4 equations come from, because rather than learning 4 equations, I'd sooner learn 1. A car sounds, so here's my car, and it's sounding 261 hertz. It approaches a stationary observer at 45 meters per second. 45 meters per second. The speed of sound in air, V, is equal to 343 meters per second. What's the frequency is heard by the observer? So I say, well, the frequency observed is equal to the frequency of the source, and it's going to be V plus V of the observer over V minus V of the source. So this is going to equal, my frequency is 261. 343 plus My observer is stationary over 343 minus my source is moving at 45 meters per second and it is approaching positive 45. If it had been traveling at 45 meters per second away, it would have been negative. So then I say, well, F0 is equal to 261 over 343 over 298. So that's going to be whatever that works out to be. 261 divided by, go back, times 343 equals divided by 298 equals, I'm getting 300.4. Cool. Last little bit. If you canoe faster than the speed of a wave on the water, you get a wake. If you're canoeing. If you're just standing there, you get ripples going out. Yeah? So what happens is if you're standing still, your ripples look like that. Imagine dropping a whole series of stones in. If you start moving to the right, you'll get ripples that look like that. If you go at the speed of the ripples in the medium, they'll look like that. If you go faster than the speed of the ripples, you go like that. And if you go really, really fast, you get like that. So you get the ripple, you get the wake. You get the wake when you're going faster than the energy can travel through the medium. And the more pointed the wake, the faster you're going. And with ripples on a water, it's a two-dimensional wake, and with aeroplanes, it's a cone of energy, a shock wave, a sonic boom. I want to characterize how fast I'm going relative to the speed of sound in the air. It's the Mach number, which is the velocity of the source over the velocity of sound. It's a fractional value. If I want to know the cone angle, or really the Mach angle, then it is, well, it's going to be the opposite, which is the velocity of sound in air times the time, divided by the velocity of source times the time, opposite over hypotenuse. The time cancels, so it's the velocity of sound in air over the velocity of the source. And it's the sine, that equals sine of the angle. And this example is basically, I know the velocity of the jet is 335. I know that the velocity of sound is 300. What's this angle? Sine the angle is equal to 300 over 335. And you work out your angle, sine to the minus 1 of 300 over 335 equals some angle, figure it out, Most common mistake is people will get V and Vs confused. Vs sounds like speed of sound. It's not. It's speed of the source. So watch out for that. Cool. Let's stop there.